All right, so we'll get the recording going. And we wanted to start here, I think, with Chapter 7, Problem 6. Okay, find an equation for the conics that are described. In the first one, we're looking at a parabola where we're given the vertex and focus. In the second one, we have an ellipse and we're just given the vertices. Okay, so let me walk you through how to do this. I think what I want to do before we start computing this is just to quickly reference our book. And we're going to look at how these conic sections are typically written. Okay, so that way we know what pieces of information we're trying to find. Okay, so the first one, we're looking at a parabola where we have the vertex and focus. Okay, so the beginning, of this section, they talk a lot about the conic sections, where they come from. There's a lot of good stuff in here. And what we end up with is a different way of writing parabolas than I think that you're typically used to, but this is a more geometric way of representing it. It's still like a y equals ax squared plus bx plus c, but the way that we write it with the square completed and so on makes it so that we can easily see things like the vertex and the focus. So this is like our standard form, y equals 1 over 4p x minus h squared plus k, where hk is the vertex and the focus is shifted over from that by p in whatever direction the parabola opens. Okay. So if I just draw a quick sketch of this parabola, so it has vertex -3, 5 and focus -6, 5. That means that the vertex from the vertex is going to open towards the focus. Okay, and it's not necessarily going to hit here at -6. I don't know where it's going to hit. Okay, but I can see, all right, I have some distance between the vertex and focus, right? That's just a distance of 3. So I know that the p that we had back here is 3. The thing about this is that this equation is given for a parabola that opens either up or down. If it opens left or right, then we want to switch the roles of x and y. Okay. And if it opens down or if it opens to the left, what we typically do is you can either not think of p as a distance, you can think of it as just a subtraction, right? So you give it as negative. Or if you think of it as a distance, then you throw a negative on there. But we know that parabolas that open down have a negative. The same is going to be true with parabolas that open to the left, right? We want a negative on that leading coefficient. Okay. All right. So we have that the p is equal to 3, and the vertex is -3, 5. So what I'm going to do is I'm going to use my general formula, -1 over 4p x minus sorry. I was writing this as the original standard, right? If we have a y equals, I would have an x here. And the h is like the x coordinate, so that goes with x's. Okay. But if I have a parabola that's opening left, right, I'm going to have an x equals a function of y, and I want my y value to be close to, the y value, the k, right? So here it's a y minus k, and then the h is on the outside. Okay. So this is h comma k. and this is the p. So we can just fill it in. So we have -1 over 4 times 3, so -1/12. Oops, I lost my squared. Y minus 5 squared minus 3. Okay. So that's all there is to that one. For an ellipse, we're going to have to do a little bit more work. So let's start by looking at the equation. So with ellipses, we have two foci. Okay, so we have a vertex at one end, a vertex at another. Here, each focus is inside the ellipse because it's bending inward. The other major thing that we talk about with an ellipse is the major axis. So that's from one vertex to another. And then we have the minor axis, which is how wide it is at its narrowest point. Okay. And when we look at the standard form, we need to know what those major and minor axis lengths are, because that figures into the equation. Right. So here's a formula for the equation of pretty much any ellipse: x minus h squared over a squared, y minus k squared over b squared equals 1. And rather than try and remember what goes where, I know that hk is the center, and the x value goes with the x, the y value goes with the y. Then the a and the b are the length of the major and minor axis, okay? But not like the whole length, right? So from the center out, right, would be b, and from the center out would be a. And you just make sure that the distance in the x direction goes with x, the distance in the y direction goes with y. And that's, how the formula is sort of created anyway. Okay. If we're given, well, let's just go from there. So let's see if we can draw this thing. Okay, so we have an ellipse with vertices 2, 4, 2, 2. Okay, so here is 2, 4, 2, 2, -2, 3, and 6, 3. Okay, so I'm going to make a lame attempt at drawing an ellipse here. Okay. So here's the center, right? So it's directly between these vertices, also directly between these vertices. I'll get the same point either way. So if I look directly between my up and down vertices, right, this is 2, 4, this is 2, 2. If I average them, right, I have the same x value, and then if I average the y's, I'll get a 3. So the center is 2, 3. Okay. And the distance in the y direction that we go up is 1. Okay. This is the point 6, 3. The distance in the x direction that we go to go from the center to the edge is 6 minus 2, or 4. So if I start with my generic equation, the center is 2, 3, so I have x minus 2 squared and y minus 3 squared. And in the x direction, from the center to the edge of the ellipse is a distance of 4, so I divide by 4 squared. In the y direction, from the center to the vertex, is a distance of 1, so I have 1 squared. Okay, so for finding an equation for the ellipse, that's it. Does that make sense? Okay. Where do you want to go from there? We can we can start anywhere you like, or if you don't have a specific question, I'll just start with the ones that I didn't post up the solutions for. I think that was just chapter 7, if I'm looking at this right. Okay, so we'll just back up a little bit. Okay, so here's chapter 7, problem 1. Find the slope of the tangent line to the parametric curve x equals t squared plus 1, y equals t over 2, at t equals -1, and at t equals +1 without eliminating the parameter. So this is two different t values. That means two different tangent lines. Okay, so I know that to find the equation of a tangent line, I need a point and I need a slope. So let's start by finding the derivative so we can output slopes. dy dx is dy dt over dx dt. And these are simple enough equations that I'll just kind of, write them in here. I won't split this off as a separate step. So the derivative of y, t over 2, that's the same as a half t. When I differentiate it, I get 1/2. The derivative of x with respect to t is 2t plus 0. Okay. So this is just 1 over 4t when I simplify. Okay, so now let's look at t equals -1. Okay, I need to find an x value. So x is t squared plus 1, which is -1 squared plus 1, which gives me 2. Y is half of t, which is half of -1, which is -1/2. And the slope is 1 over 4 times -1, which is -1/4. So I have a slope, I have a point, I can write down the equation of the tangent line. So y minus -1/2 equals the slope, x minus 2. So y plus 1/2 equals -1/4 x plus 1/2. And then I subtract a half from both sides, and I get y equals -1/4 x plus 0. Okay, maybe I went through that one too quickly. Maybe I'll write out a little bit more for this next one. So let's look at t equals 1. So x is going to equal 1 squared plus 1, which is 2. Y is a half of t, so I plug in half times 1, and I get 1/2. Okay, so that gives me my xy point. Then I'm going to find the slope. Slope is 1 over 4t, so when I plug in 1, I'll get 1 over 4 times 1, or 1/4. And now we use the point-slope formula to write down the equation of the tangent line. So we have y minus 1/2 equals 1/4 x minus 2. I'll go ahead and distribute the 1/4. So y minus 1/2 equals 1/4 x minus 1/2. And now I'm going to add a half to both sides. So we get y equals 1/4 x plus 1. All right. Any questions on that one? Good, good. All right. This next one, find both the first and the second derivative at t equals 2 for the parametric curve x equals 1/2 t squared, y equals 1/3 t cubed. Okay, so let's start with dy dx. That's dy dt over dx dt. Okay, dy dt, when I differentiate this, the 3 comes down, a third times 3 cancels, so I'll just get t squared. For dx dt, when the 2 comes down, it cancels with the half, so I just get 1 times t. When I simplify this, t squared over t, I just get t. Okay, so dy dx at t equals 2 will give me 2. So that's my first answer. All right, now for the second derivative, what I want to do is treat the first derivative as my function. So I'm going to take the derivative of dy dx divided by dx dt. Okay, so instead of differentiating y, I'm differentiating y prime. Okay, so we're going to take the derivative of t in the numerator, and dx dt we already wrote down. Dx dt is just t. The derivative of t is 1. So the second derivative formula is 1 over t. So then if I want to evaluate the second derivative when t equals 2, I'll get 1/2. All right, any questions on that one? Okay, so again, these are pretty simple equations to work with. The whole point is just figuring out what goes where. That's sort of what's being, I want you to think about, if that's what I'm emphasizing in the review, that's what I want to test on, right? We'll leave the heavy algebra for other sections. All right, find the values of t and the xy points on the graph of x equals cosine 3t, y equals 2 sine of t, where the tangent line is either horizontal or vertical. All right, the first thing that I'm going to do, we'll look at a graph of this later, but you don't need to look at a graph to solve the problem. So what I'm going to do first is I'm going to find out the derivative dy dx. So again, that's dy dt divided by dx dt. The derivative of y with respect to t is going to be 2 cosine t. The derivative of x with respect to t is going to be, when I differentiate cosine, I get negative sine. Inside stays the same, and then I multiply by the derivative of the inside stuff. Okay, so I get negative 2 cosine t over 3 sine of 3t. Be very careful here that arguments are different, so don't just think cosine over sine is cotangent, because you have to have cotangent of something, and it's not cotangent of t because it's not sine of t, and it's not cotangent of 3t because it's not cosine of 3t. Okay, so these two don't mix. All right, if I want to figure out where a tangent line is horizontal, a horizontal tangent line has a slope of 0. So I want to figure out where the derivative outputs 0. So I'm going to solve dy dx equal to 0. And as we've talked about before, a fraction is equal to 0 when the numerator is 0. So this is going to be when negative 2 cosine of t is equal to 0. Okay. So when I solve this, I'll get cosine of t equals 0. So t is inverse cosine of 0. When I do inverse cosine of 0, I think of my unit circle. Okay, 0 is the x value. So inverse cosine will be this angle pi over 2. Or I could get the opposite of that, right? If I were to measure down this way, this point also has an x value of 0. So I could have negative pi over 2. Okay, plus 2k pi. All right, so these are t values where the derivative is 0. So now let's say, well, what points on the graph would I get from that? Okay, and the graph here, we'll look at it later, but because I know I have a cosine and a sine, I think that these are going to be periodic, because those functions are periodic. I think that the graph is going to start overlapping itself at some point. Okay, so we're probably only going to get finitely many answers, right? And if I look at, as an xy point, when t is pi over 2, x's cosine of 3 pi over 2, okay, cosine of 3 pi over 2 is 0. And y is going to be 2 times the sine of pi over 2. Sine of pi over 2 is 1, so this will give me 2. So I have the point 0, 2. Okay. If I add 2 pi to this, we're looking at 5 pi over 2. X is going to be the cosine of 3 times 5 pi over 2, or 15 pi over 2. Okay. 15 pi over 2 is like 14 pi over 2 plus pi over 2, so it's 7 pi, and then another half pi. Okay, so 6 pi lands me back where I started, and then I have another 7, and another half, so our x value is 0. Okay, y is 2 times the sine of 5 pi over 2. If I take the sine of 5 pi over 2, I've gone a full circle and then pi over 2 more, so that's going to give me 1. So I end up with the same point. Okay, so I don't get another point here. And we'll try one more just to be careful. So I'll add another pi over 2 to this. Okay, so another 2 pi to this. So another 4 pi over 2 added to 5 pi over 2 will give me a 9 pi over 2. So x is cosine of 9 pi over 2, which gives me 0. Y is 2 sine of I'm sorry. For my x, I need to multiply by 3, so this will be 27 pi over 2. Okay. Cosine of 27 pi over 2 is still 0, although I'm going to double check just to make sure I'm not messing anything up in my head. Okay. And then y is 2 times the sine of 9 pi over 2. Okay, and I get that same point again. All right, so now let's look at the running out of space. Let's look at t equals negative pi over 2. Okay. X is going to be the cosine of 3 times that, right? Where x is 3 cosine of 3t. So I'll get cosine of negative 3 pi over 2. Which is 0. Y is 2 times the sine of just t, so just negative pi over 2. The sine of negative pi over 2 is negative 1. When I multiply it by 2, I'll get negative 2. Okay. So these are the places where the tangent line is horizontal. Okay, we should probably check a few more t values, but I'm running out of space there, so I'll just say, trust me on it, it's just going to repeat. All right, so now let's look at part B. find out where the tangent line is vertical. The tangent line is going to be vertical when I get a 0 in the denominator. So here I'm going to solve dy dx undefined. So I'm going to get 3 times the sine of 3t equals 0. Okay, so sine of 3t equals 0. So when I take the inverse sine of both sides, the inverse sine of 0 is 0 plus 2k pi. Or I could have pi minus 0, which is just pi. And now when I divide by 3, I get t equals 0 plus 2k pi over 3, or 2/3 k pi. And for this equation, when I divide by 3, I'll get pi over 3 plus 2/3 k pi. Okay, so again, I'm going to make a little chart here where I try some t values and I see what points do we output. Okay, so when k is 0, I'll just get t is 0. Okay, so x is going to be cosine of 0, which is 1. Y is going to be 2 times the sine of 0. Sine of 0 is 0. So I get the point 1, 0. Okay. When k is 1, I'm going to get t is 2 pi over 3. Okay. 2 pi over 3 times 3 will give me a 2 pi. So this is cosine of 2 pi, which is 1. And 2 times the sine of 2 pi over 3. The sine of 2 pi over 3 is a positive root 3 over 2. So we get root 3 here. So here I get the point 1 comma root 3. Okay. So now let's look at what happens when k is 2. Then we're going to have a 4 pi over 3. Okay. So x is cosine of 3 times that. 3 times 4 pi over 3 is 4 pi. Cosine of 4 pi is 1. Okay. When I put in 4 pi over 3, I'm going to get a negative root 3 over 2 in the sine function. So we end up with a negative root 3, so we have 1 comma negative root 3. Okay. So this is k is 0, 1, 2. Now let's look at when k is 3. So then I'll just have t is 2 pi. Okay. When I multiply that by 3, I get 6 pi. Cosine of 6 pi is 1. Sine of 2 pi is 0. So I have 1, 0. That's a point that we've already had, and it's going to start repeating at this point. All right, so that was solutions to our first set of solutions. Now let's look at pi over 3 plus 2k pi. So when k is 0, I'll get pi over 3. When I multiply by 3, I'll have pi. Cosine of pi, I remember we just have cosine of 3t. So cosine of pi is negative 1. Okay. For our sine function, when I put in sine of pi over 3, I get root 3 over 2 times 2 will give me a root 3. So we have negative 1 comma root 3. Okay. All right, when k is 1, we have pi over 3 plus 2 pi over 3. That gives me 3 pi over 3 or pi. When I multiply by 3, I will have 3 pi. I plug that into cosine. cosine of 3 pi is -1. When I take sine of pi, I get 0. So we have -1, 0. When k is 2, we'll have pi over 3 plus 4 pi over 3, which gives us 5 pi over 3. So now I plug in t as 5 pi over 3. When I plug into my x equation, I multiply it by 3, so I'm going to take cosine of 5 pi, which is -1. When I take sine of 5 pi over 3, I get -√3 over 2. So we have -1 comma -√3. Okay, so this was k equals 0, k equals 1, k equals 2. Now let's look at when k is 3. I'll have pi over 3 plus 2, the 3's will cancel, so plus 2 pi. So we'll have 7 pi over 3. Okay. When I plug into x, we multiply by 3. So I'm going to take cosine of 7 pi, that's -1. When I plug in for y, I take sine of 7 pi over 3, which is √3 over 2. When I multiply by 2, I'll get √3. So I have -1 √3, and now we've started repeating ourselves again. So I get these 6 points where the tangent line is vertical. So now let's go ahead and take a look at the graph and see if our results make any sense at all. So I want to graph cosine of 3t. Let's make sure I'm in the right mode. Radian, parametric. Okay. Cosine of 3t and 2 times sine of t. All right? Yep. Okay. So I look at the graph and I get this neat little wiggle thing. Okay. When I look at the graph of this, I can see I'm going to have a point down here where the tangent is horizontal and a point up here where the tangent is horizontal. Okay. And we did find these 2 points, 0, 2, and 0, -2. Okay. That looks like it lines up pretty nicely. And then for vertical tangent lines, it looks like on this curve, on the outside edge, I'm going to get a vertical tangent, and then also here and also here. Okay. So all of these are going to be at some negative value. Okay, turns out that that's, I guess, -1. All right, and I get these 3 of them, right? -1 √3, -1 0, -1 √3. We can try to trace along, see if that matches up. So looks like on this edge, -1 and then 1.732 is √3. Okay, so when I graph this on my calculator, the answers that we get match up, and that's a good thing. All right, any questions on this one? All right, so this is a good example of a problem where you have to really keep things straight and be careful. There's a lot of solutions. You don't want to lose any. All right, problem 4. Find the area of the region enclosed by this cardioid. So on the last one, we solved the whole problem, and then we used the graph to sort of make sure that we did it right. For this one, I'm going to go the other direction. I think that it's really beneficial to look at a graph and sort of see what it is we're trying to do first, so that I think it gives us a nice guide. Okay, so this is polar coordinates. So I'm going to go ahead and draw my graph in polar. Okay, and the equation is 2 plus 2 cosine theta. So I graph and I get this hypercardioid, right? Because it's a heart shape, except sideways. And it says find the area of the region enclosed by this. So I want just the area of all of this, okay? So what I can do is I can say, well, we want to think about rays coming out of the origin and sweeping out all of the area, okay? So if I hit trace, it'll give me an XY coordinate, but also tell me the theta. I can see, all right, as I trace along, there's my angle, right? Getting here at an angle of pi over 2. And as I approach an angle of pi, it's coming back into the origin. And when I extend beyond an angle of pi, it's, it's kind of lining up with what you'd expect, right? In this case, our, one loop around gives us everything. Okay. And that makes sense because I have a cosine of theta. It's not a 2 theta or 3 theta or anything like that. So the period is just going to be 2 pi. You do have to be careful, though. Sometimes some of the graphs will get swept out in just a 0 to pi interval. Okay, so I want to remember my area formula. And actually, I think, is this one of the ones that was given? Yeah. For polar equation, we're given the area formula, the integral from alpha to beta of 1/2 r squared d theta. Okay, so it's handy now that I know the limits of integration. I'm going to go from 0 to 2 pi, 1/2, and then I take my r formula, 2 plus 2 cosine theta, and square it. Okay, so that's the integral we want to work out, and that's, at this point, I think kind of nice. There's just this one variable theta, so there's nothing crazy going on. I can just evaluate this integral now. Okay. So when we FOIL out this inside, 2 times 2 is 4. Then I have 2 times 2 cosine of theta. Right, so I have outers and inners, so I'm going to get that 4 cosine of theta twice. And then the last 2 cosine theta times 2 cosine theta will give me a 4 cosine squared theta. Okay. So let's go ahead and distribute that half. So then this will be a 2. 4 cosine theta plus 4 cosine theta is 8 cosine theta times a half gives me 4 cosine theta. And I'll have a 2 cosine squared theta. All right, to evaluate this integral, there's no signs in here, so I can't do a u substitution. I can integrate 2 easily enough. I can integrate cosine theta easily enough. So I'm going to break those off and integrate cosine squared theta separately. Okay, so this is an integral that we've seen a few times back in our integration chapter. When I integrate trig functions and I have even power and I don't have the odd power of the other one, I don't have an odd power of sine, I need to reduce the power by 1. So I'm going to use that power reduction formula. Cosine squared theta is 1/2 plus 1/2 cosine of 2 theta. And I think that was one of your identities that's provided on the exam. Okay, cosine squared theta, yeah, here it is, 1/2 plus 1/2 cosine 2 theta. Okay. All right. So then when I distribute the 2, those the 2's and the halves will cancel nicely. And then I can integrate. When I integrate 1 d theta, I will get theta. When I integrate cosine of 2 theta, I get a positive sine of 2 theta times a half. Okay, because what I'm doing here, we've done this a number of times, I'm shortcutting a u substitution, right? Because my inside is 2 theta. I know if I differentiate, you'd multiply by 2. When I integrate, I'm going to divide by 2. Okay, so when I plug in, I'm going to get 2 pi plus 1/2 sine of 2 times 2 pi, which is 4 pi, minus 0 plus 1/2 sine of 0. Okay, so sine of 0 is 0, sine of 4 pi is 0, so we just get a 2 pi on here. Okay, now let's look at the easy side. Okay, so I have the integral from 0 to 2 pi of 2 plus 4 cosine theta. I can just integrate that as it is, so I'm going to get 2 theta plus 4 sine theta. Okay, and so when I plug in, I'm going to get 2 times 2 pi plus 4 sine of 2 pi minus 2 times 0 plus 4 sine of 0. 2 times 2 pi is 4 pi. Sine of 2 pi is 0. Minus 0. Sine of 0 is 0. So I have 4 pi plus 2 pi. And then when I combine those together, I will just get 6 pi. Okay, so be careful not to lose your pieces when you break a problem up into pieces. Any questions so far? All right, so here we have another area problem with polar. Find the area of the region common to all 3 of the circles. So I'm going to go ahead and graph this so that we can see the 3 circles. So our first graph is r equals 1. The second one is r is 2 cosine theta. And then I have r is 2 sine theta. Okay, so blue, red, and black. So I'm going to find these. All 3 of these are actually circles, right? That's what it tells me in the problem. And I want to find the region, the area of the region that's inside all of them. Okay, and that's going to be this region in here. So I'm going to go ahead and sketch a graph of this so we can draw on it a little bit. Okay, so here's my axes. So I have this circle r equals 1. Okay. I have this circle r is 2 cosine theta. And then I have this circle, r is 2 sine of theta. Oh. Close enough. Okay, So then if I sort of highlight here the region common to all three, that's this region here. And the first thing I need to do is figure out what are the limits of integration for that region. Now remember the way that polar integrals work. Polar in general, I'm thinking about, rays coming out of the origin. So when we integrate, what we're doing is we're thinking about, take a ray coming out of the origin and it sweeps out the area that we get. Okay, so what I need to do is say, well, I'm going to start at an angle of 0 and I'm going to keep going up. Here, let me break this up. I'm breaking this up into three regions, right? So I have region 1, region 2, and region 3. For region 1, the region is bounded by, it starts at the origin and it goes out, if I draw rays coming out, until it hits this blue circle. Well, this is blue because I highlighted the pink. But it goes out until it hits this pink circle. Okay? So area 1 is going to be an integral that starts at an angle of 0 and goes up to whatever angle gives me this point, and I'm integrating 1/2 r squared, where my r is the r given by this pink circle. So that's 2 sine of theta. Okay. Area 2 is going to, if I think about rays, I start at the origin and I go out until I hit the green circle. The green circle is r equals 1. So this is going to be 1/2 times 1 squared d theta. And it's going to pick up where area 1 stopped, and it'll go to this other intersection point. We'll come back and get the intersection points in a second. Okay, then area 3 is going to start wherever area 2 left off, and these rays are going to go out and hit the brown circle, which is r equals 2 cosine theta. Okay, so now let's find these intersection points. So this first intersection point, maybe I'll call this point B, call this one point C. So point B is where the green circle and the pink circle intersect. So what I want to do is find an angle where I get the same radius from the green and the pink. So I set the two equal to each other. 1 equals 2 sine theta. So 1/2 equal, oops, 1/2 equals sine theta. Take the inverse sine of both sides. Inverse sine of 1/2 will give me a pi over 3 plus 2k pi, or pi minus that, right? So, or 2 pi over 3 plus 2k pi. But I can see from my sketch, I want, this pi over 3 looks like it's going to do it. Okay, and if I plug that in, I do indeed get a solution. So I want the theta to be pi over 3. So that means that that's where my first region stops, and the second one starts. Okay. To find point C, that's where the green circle and the brown circle intersect. So r equals 1 and r equals 2 cosine theta, so 1 equals 2 cosine theta. So 1/2 equals cosine theta. When I take the inverse cosine of 1/2, I get pi over 3. I messed that up. Be careful doing unit circle in your head. The sine value that gives me 1/2 is pi over 6. When I take pi minus that, I get 5 pi over 6. Okay. The 5 pi over 6 is in quadrant 2. So that's this intersection point over here that I don't care about. All right, so here I get pi over 3 plus 2k pi, or negative pi over 3 plus 2k pi. Right, and that corresponds to this intersection and this intersection. But again, it's only the one in the first quadrant that I'm really concerned with. So pi over 3 is my second limit of integration. Okay, in this area 2. So in the area 3, that's where I start, and it'll finish when I get the rest of that area. Okay, and that's going to be the rest of quadrant 1. So it's going to go up to pi over 2. Okay, so now I have the setup done, and we just need to go ahead and do the integration. Okay, so let's look at area 1. So that's the integral from 0 to pi over 6. I'm going to shortcut this a little bit. I'm going to go ahead and FOIL this out and distribute a half. So when I FOIL it out, I'm going to get 4, there's no foiling. It's just 4 sine squared theta times a half. So I get 2 sine squared theta. Sine squared is the same story as cosine squared. I need to use my identity, right, that we have here. Sine squared theta is 1/2 minus 1/2 cosine of 2 theta. That's not a typo. Both of these give you a cosine of 2 theta. That comes from the double angle identities for cosine. Right? So I get 2 times 1/2 minus 1/2 cosine of 2 theta. And I distribute the 2's, that'll cancel the halves. So I'm integrating 1 minus cosine of 2 theta. So I'm going to get theta minus 1/2 sine of 2 theta. When I plug in pi over 6, we'll have pi over 6 minus 1/2 sine of 2 times pi over 6, which is sine of pi over 3. And then minus, when I plug in 0, I'm going to get 0 minus 1/2 sine of 0. Sine of 0 is 0. Okay, so here I get pi over 6. Sine of pi over 3 is root 3 over 2 times a half is root 3 over 4. Okay, let's look at area 2. That's the integral from pi over 6 to pi over 3, 1/2 times 1 d theta. So I get 1/2 theta. So when we plug in, I'm going to get 1/2 of pi over 3 minus pi over 6. Pi over 3 is 2 pi over 6 minus pi over 6 will give me a pi over 6 times a half gives me pi over 12. Okay, and then for area 3, we're integrating. I'm going to, well, let's look at what we're integrating first. Okay, so I'm integrating from pi over 3 to pi over 2, and I'm going to have 4 cosine squared theta times a half, so I'm going to have 2 cosine squared theta d theta. And just a minute ago, we integrated cosine squared theta. In fact, we integrated 2 cosine squared theta. Okay, and when I integrated 2 cosine squared theta, I ended up with theta plus 1/2 sine of 2 theta. So I'm just going to reuse that a little bit. That was plus 1/2 sine of 2 theta. Going from pi over 3 to pi over 2. Okay, so when I plug in pi over 2, I get pi over 2. Pi over 2 times 2 is pi. Sine of pi is 0. When I plug in pi over 3, I'm going to get pi over 3 is 1/2 sine of 2 times pi over 3. Sine of 2 pi over 3. It's actually the same as pi over 3, sine of pi over 3, which is root 3 over 2. Okay, so we get pi over 2 plus 0 minus pi over 3 minus root 3 over 4. Okay, so then the total area is going to be area 1, so I have pi over 6 minus root 3 over 4 plus pi over 12 plus pi over 2 minus pi over 3 is 3 pi over 6 minus 2 pi over 6, which is pi over 6. Okay, so I have pi over 6 plus another pi over 6. This is 2 pi over 12 plus 2 pi over 12 is 4 pi over 12 plus another one is 5 pi over 12 minus root 3 over 4 and another root 3 over 4. Give me a root 3 over 2. Okay, so that is the total area. All right, that one, a lot of plugging into trig functions, but the setup, I think, was the tricky part and the part that I want you to focus your most attention on. Are there any questions over that? Okay, so that's it for problems that didn't have answers attached to them. The rest of the problems have answers but not worked out solutions. So is there anything that you want to go over off of the rest of the review in more detail than just having an answer? Am I going to attach a unit circle to the test? Well, I wasn't going to, but I guess I could add that. I could add a little one. I could probably squeeze one in here, and that won't add another page, so it'll be fine. Sure, I'll throw a unit circle on there. All right. Any last questions? Well, if not, we can always add more in when we have class tomorrow and we go over some more review stuff. So we'll call that it for now, and then we'll answer more questions in class tomorrow.